Hi, my name is Manmeet Gill and I'm going to be talking about acid and base equilibrium. There are three common definitions of acids. Arrhenius acid is any substance that increases the concentration of hydronium ions in solution. A Bronsted-Lowry acid is any substance that can act as a proton donor. And a Lewis acid is any substance that can accept a pair of electrons. What makes a strong and weak acid? By definition, a strong acid is one that completely dissociates in water. In other words, 1 mole of the generic strong acid HA will yield 1 mole of hydronium, 1 mole of the conjugate base, with none of the protonated acid HA remaining in solution. In contrast, a weak acid will be less willing to donate its proton and will only partially dissociate in solutions. Here I have a list of a few strong acids, so hydrochloric acid, nitric acid, and then we have some weak acid, oxalic acid and sulfurous acid, and more. So the definition of a base. Again, there are three common definitions of a base. The Arrhenius base is any compound that donates a hydroxide ion in solution. A Bronsted-Lowry base is any compound that is capable of accepting a proton, and the Lewis base is any compound capable of donating an electron pair. So one thing to keep in mind about basic solutions in water is that they will have a pH between 7 and 14. So what makes a strong base and a weak base? A strong base is the opposite of a strong acid, whereas an acid is considered strong if it can donate protons. A base is considered strong if it can easily deprotonate from other compounds. And in contrast, a weak base is one that only partially is willing to give ions in the solution. So over here in the diagram, we can see that the weakest base is perchlorate ion, and the strongest will be the hydroxide. Throughout this presentation, I will be referring to the Bronsted-Lowry definition of acid and bases. So moving along, what is equilibrium? Acids and bases have chemical equilibrium in solution. At chemical equilibrium, the product and reactants have reached a state of balance, although reactions may still be taking place within the sample, but the forward reaction and the reverse reaction are taking place at the same rate. So the concentrations of the product and the reactants is not changing at all. The equilibrium constants. The equilibrium constants of acids and bases can be used to determine the strength of a compound. These constants can also be referred to as dissociation constants or the ionization constants. They can be used to calculate the percent ionization of an aqueous solution or to determine the pH. This would be the acid ionization constant, and in this equation, the concentration of HA is the concentration of the acid, and the concentration of A is the concentration of the conjugate base, and the concentration of H3O is the concentration of hydronium. And that is the base ionization constant, and for this equation, the concentration of B is the concentration of the base, the concentration of BH is the concentration of the conjugate acid, and the concentration of OH is the concentration of the hydroxide. You may be wondering, how are these two constants related? When the two equations previously mentioned are multiplied, you get the equilibrium constant, or the dissociation constant for water. Over here, we can see how that is done mathematically. And so A cancels out with A, HA cancels out with HA, and then we are left with the hydronium ion and the hydroxide, and multiplying that will give us the equilibrium constant. What is a pKa value and how does it relate to acids and bases? By definition, the pKa value tells us the extent to which an acid will react with water, the base, but in more depth. We can also calculate the equilibrium constant for a reaction between any acid-base pair. Mathematically, it can be shown in the first equation. And over here, the delta pKa is the pKa of product acid minus pKa of reactant acid. So in this equation, it's both of these are given, and I recommend you guys pause, and I will be saying the answer in a few right now. So the answer for this would be 6.3 times 10 to the 5. In problem number 1, we'll be calculating the concentration of the hydronium ion and the concentration of acetic acid ion in a molar concentration of 0.1. Just by looking at the equation, we know that NaCH3COO dissociates completely, and acetic acid ion produced by the dissociation of NaCH3COO is taken into account by using 0.1 moles per liter for the initial concentration. Looking at the ICE table, we have the initial concentration of acetic acid as 0.1 moles per liter, and the concentration of acetic acid ion is equal to 0.1 moles per liter as well. We're going to be using the equation of acid ionization constant, and so we're going to get this concentration of hydronium times the concentration of acidic ion over the concentration of acetic acid, and we're going to get x times 0.1 plus x, and at the bottom is going to be 0.1 minus x. Then it's going to be x times 0.1 over 0.1, but 0.1 and 0.1 cancel out, and therefore x is equal to 1.8 times 10 to the power of negative 5. So in the end, the concentration of hydronium is 1.8 times 10 to the negative 5, and the concentration of acetic acid ion is 0.1 moles per liter. Moving on to problem number 2, we're going to be calculating the equilibrium constant and the percent ionization of HA in a 1 molar concentration at room temperature, assuming that Ka is equal to 1.0 times 10 to the power of 5. So we're going to be writing out our equation as I've already done, and the initial concentration of HA is 1 and 0 for both hydronium and A, and to completion the concentration of A and hydronium is 1 mole per liter, and for HA it is 0. And to the left, we're going to be adding x, and for both A and hydronium, we're going to be subtracting x. So we get the shown equilibrium concentrations. We're going to be setting up the acid ionization constant equation. So we know that the concentration of both A and hydronium, but not of HA. So we replace that with x, and we're going to rearrange the equation for x as we've already know the acid ionization constant, and so we get that the x is equal to 1 times 10 to the power of negative 5. And over here we need to determine the percent ionization, so we know that the fraction of HA that remains at equilibrium is calculated by 1 times 10 to the power of negative 5 divided by 1 molar concentration times 100, and we get that as 0.001%. Therefore, the percent ionization of HA is 99.99%. In conclusion, these are my references, and thank you for watching my presentation.